So having talked about the different kinds of forces, the intramolecular forces of attraction and the intermolecular forces of attraction, which I believe you should be able to differentiate at this point, let's look at solutions and their properties. So we'll begin first of all by looking at what a solution is and just a few things about it. So I believe a solution is not something that is new to most of you. So a solution is basically just a combination of a solvent and a solute. Okay, so I want you to pay particular attention. So a solvent is usually, and I'm using the word usually or mostly, not that it can only be a liquid. A solid usually a solid, but not always a solid. So solutions can be combinations of liquids, combination of a solid and a solid can still be called a solution. But for the sake of understanding, I want you to think of a solvent to be a liquid and then a solid to be a solid, just for understanding's sake. Okay, so a solution is a combination of a solvent and a solute. In other terms, we can put it this way: a solution is a mixture of two or more pure substances. And I think that's what proves to say two pure substances can be liquids, solids, gases. Okay, so don't restrict a solution to a combination of a solid and a liquid. It would be better you use solvent and solute, or say a mixture of two or more pure substances. That's what a solution is. Alright, so we'll talk about the Henry's law of solubility. The argument that Henry made was that the solubility of any given gas is directly proportional to the partial pressure of that gas. So G subscript G is denoting the gas, and then K there is denoting the constant. Okay, so the solubility of a gas increases as the partial pressure of that gas increases. That's Henry's law of solubility. And of course, earlier I've mentioned that pressure has got a effect on the solubility of a gas, but less effect on the solids and liquids. So picture this. Let's assume this is a bottle. Don't mind the drawing. And then we have water. Okay, to that level. And then the top part occupied with carbon dioxide. So now assume you begin pumping more of the carbon dioxide into the container. When do you expect that more of the carbon dioxide would be dissolving in water? So the way it is the carbon dioxide that is in contact with water will be able to dissolve into water. Okay, so the more pressure you exert or the more carbon dioxide you add, there will be more pressure, there will be an increase in pressure, so you expect that more carbon dioxide will actually dissolve in water. Of course, there will be a point where no more carbon dioxide can actually dissolve. There will be some carbon dioxide leaving in the water as well as dissolving in water. At that point, we refer to that point as an equilibrium point. Okay, but understand that that is the formula. Solubility increases as you increase the partial pressure of a gas. So of course, you know that the partial pressure is like the pressure of a gas in comparison to a total pressure. Okay, so partial pressure can be determined as the mole fraction of that gas multiplied by the total pressure in the container. That is in a case where you've not been given what? You've not been given the partial pressure. But in most of the cases, for your calculations, the partial pressure will just be equal to a total pressure, in that there will be no other gas exerting pressure in a container. Okay, hopefully you understand what I mean by that. So let's look at a practice question and understand how we basically get to apply Henry's law in terms of performing calculations. So Actually, in some textbooks, you find that instead of using S with a subscript G, they can use CG to denote the formula for Henry's law. Okay, let's look at the questions that we have now. So a certain soft drink is bottled so that at 25 degrees Celsius, it contains carbon dioxide. Okay, so at a pressure of 5 atm over the liquid. Okay, assuming that the partial pressure of carbon dioxide in the atmosphere is that, and then calculate the equilibrium concentrations of carbon dioxide in the soda both before and after the bottle was opened. The Henry's law constant for carbon dioxide in aqueous solutions is that. Okay, so let's take note of the data we've been given. So K is equal to, which is a constant, 3.1 times 10 to the power negative 2 moles per liter. Then the other piece of information we've been given in the question, we've been given the pressure to be 5 atm inside the bottle, I believe, 5 atm. So 5 atm, that is before opening. So inside the bottle of that soft drink, we have 5 atm of pressure. So we can call that, because we are told to calculate, because the certain soft drink is bottled, so what it contains. So inside the bottle, that is before. And then after, in the atmosphere, after you've opened, the pressure will be coming from the atmosphere, which is now 4. Okay, so let's now try to determine the equilibrium concentrations. So the concentrations, the equilibrium concentration, in other terms, is the solubility. Okay, how much of the gas is present in what? How much of the gas is present in the solution is the solubility. Okay, so let's try to perform the calculation. The equilibrium concentration is just the same as the solubility. So to determine the solubility at these two different partial pressures, that is before the bottle was opened, before. So the solubility of carbon dioxide, we can use Cg to denote the concentration. So the Henry's constant was 3.1 times 10 to the power negative 2. Now I need to mention there is also L dot ATM there, which makes sense actually. So that means we have moles and then divided by L dot ATM there. So if we get to multiply by the pressure, you notice that the ATM will basically gets to go away, and then you only remain with mole per liter, which is a smaller concentration. So 3.1 multiplied by 5, of course, times 10 to the power negative 2. So we get to have 0.155 with the molar concentration there. Okay, so take note of that value before opening, and then after opening we need to apply the pressure, the atmospheric pressure, the atmospheric partial pressure of the carbon dioxide. So 3.1 by 10 to the power negative 2 multiplied by 4 by 10 to the power negative 4. So we get to have 1.24 times 10 to the power negative 5 molar concentration. Okay, so what have you seen? So inside the bottle where we had the higher partial pressure, the concentration was higher. Outside, after opening the bottle, the partial pressure of the carbon dioxide in the atmosphere was low, which also led to less solubility or less concentration in the solution. So that is the conclusion of Henry's law. Just be able to remember that the solubility of the concentration of the gas is directly proportional to the partial pressure of that gas. So let's talk about how we get to convert from molar concentration to molar concentration. So we know molar concentration stands for, we can actually use a small letter m to denote it, which of course means the moles of the solute divided by the kilogram of the solvent. And then on the other hand, molar concentration is moles per liter of the solution. So there's a difference here. Here it's kilogram of the solvent, and there is the liter of the solution. Okay, on top we're referring to the number of moles. Of course, for the molar concentration, it's capital letter M, which is actually the commonly used one. Okay, so we'll consider two examples to just help us understand the concept behind the conversion. So let's take it, we have 8.01, okay, small letter m, which indicates molar concentration of sulfuric acid. So the question is, taking or given that the density of the resulting solution was, so our density was 1.354 grams per milliliter. Okay, taking that to be our density, we need to find the molar concentration. Okay, so how do we find the molar concentration? So one thing that we know is that the molar concentration, where we want to go, the units are moles per liter. Okay, now where we are starting from, we have moles per kilogram of the solvent. Okay, so we need to ensure we know how much of a solvent we add. So the simplest way is to take an assumption that we add a kilogram of the solvent. So that would mean that where we are starting from, we have 8.01 moles of the sulfuric acid in a kilogram of solvent. Okay, so that means that at the start we already have our number of moles. So the only thing that we need to determine here is now the volume of the solution. So how basically can we find the volume of the solution? How can we find the volume? So since we've been given the density to be 1.354 grams per milliliter, so now the milliliter is a volume. So if we want to get to a point where we find the volume, we need to ensure that we get to find the mass for the solution. Since we already have a density, if we find the mass of the solution, we will be able to find the volume. Remember, density is equal to mass over what? Mass over volume. So if you have the mass of a solution and the density, you're able to find the volume. So our goal is to find the mass of what? The mass of the solution. So how do we find the mass of the solution? How do we find the mass of the solution? Okay, so one way is, since we know the moles of the solute, which is the sulfuric acid, since we know we know the number of moles of that solute, we can basically get to use the molar mass to find the mass, right? So 8.01 moles of sulfuric acid. Now the molar mass of sulfuric acid is 98.0768. I believe you know how to find the molar mass. That's not something that you should have challenges with. So grams per mole. So you can see that the number of moles will basically do cancel out. So what you're going to get is the mass of the solute. So the mass is 785.6 grams of our solute. Now we need to find the mass of a total solution because the density we're given was the density of the solution. So how do we find now the mass of a solvent? Now the mass of a solvent, from the start we took an assumption that it's a kilogram. So kilogram, if you take it to grams, you know that a kilo stands for 10 to the power 3, so we have 1000 in grams. Okay, so if we are to find the total mass, we need to add the 2. So adding the 2 will give us 1785.6 grams. So we found now the mass of the solution after finding the mass of the solute and the solvent. The solvent was an assumption, the solute was calculated using the number of moles and also the molar concentration of, the molar mass of sulfuric acid. Okay, so now at this point, since we've got the mass and the density, so we know density is equal to mass over volume. So if you have to make the volume the subject, volume becomes mass divided by the density. So this mass divided by 1.354 as our density. Okay, so after dividing, of course the grams will cancel out, so the volume that we're getting is 1318.76. The units of the volume, don't forget, you get from the density, in this case milliliters. Okay, so now we've gotten the information that we needed. We needed the number of moles and also the volume. Now the volume is needed in liters, so milli stands for 10 to the power negative 3, so tas times 10 to the power negative 3 now in liters. So that is our volume. Then we divide it into what? Into the number of moles, which were 8.01 moles, with an assumption of a kilogram of a solvent. So grab your calculator there and then just try to divide. So the value I'm getting is 6.07 6.073 in what? So actually it's 39, which makes it just 4. Now the units are molar concentration. Okay, that's how we can easily convert from molar concentration to molar concentration. Maybe for the sake of practice, try to practice. Just try out 21.4 molar concentration of hydrogen fluoride there. Okay, so here take the density. So whenever you see that denotes the density, take the density of the resulting solution to be that. Okay, so how do you basically get to find the molar concentration? So just under solutions, we just want to now talk about the colligative properties. So we already know that a solution is made up of solutes and also solvents, right? So now, what are these colligative properties? So colligative properties are defined to be those properties of a solution that depend on the number. So the key term there is depend on the number of the solute particles and not the identity of the solute particles. So the key term here is, of course, the properties that depend on the number of the solute particles and not the identity. So what that means is, if you're trying to perform a calculation or trying to determine that property, you don't have to ask yourself what material it is. All you just have to do is just look at the number. Okay, so colligative properties don't depend on the identity of the solute, it just depends on the number of the particles of a given solute. Okay, so those are what we call colligative properties. So in this video, I'll explain for you vapor pressure, boiling point derivation, melting point depression, and osmotic pressure as colligative properties. Okay, so starting with the first one, called vapor pressure. So I'll make sure that these colligative properties make sense and simplified to the core. So what exactly can you think of vapor pressure? Vapor pressure. So obviously if you look at vapor pressure, the simpler way you can look at it is vapor. So we know what pressure is. So vapor pressure. So it is a pressure that is being exerted by the vapor. So I'll give you this example. Let's assume we have this as our container, right? Cylindrical, not cylindrical, that is spherical container, right? And then we fill it with a liquid to that level. So vapor pressure in this container will be the pressure exerted by the gas particles, or in other terms vapor. Okay, of course there are many, you can use a different device like a manometer to measure just that vapor pressure, but look at the vapor pressure there. So now this vapor pressure can be affected when you basically get to add a solute. You add solute particles to that liquid. So if you add the solute particles to that liquid, what basically do you expect? So what is going to happen is this: you're going to have, and especially if this is a very heavy solute placed into that liquid. Now remember, from the start of the lesson under solutions, we did emphasize to say for a solution to be formed, there are intermolecular forces of attraction between the solute and the solvent. So that solvent that we have there is going to be, there are going to be attractions between the solvent and the solute particles that we are adding. Okay, so now that will cause less of the solvent to become vapor, meaning that there will be less vapor there. It is not easy for the solvent particles to become vaporized or get into the gaseous form, so less of it will be there. So that will lessen or reduce the vapor pressure of that solvent. Okay, so what are we trying to say? So what we're trying to say is, if you basically get to add a solute that is of course argumentatively a non-volatile solute, okay, that is of heavy, okay, it is going to affect the amount of the solvent that vaporizes, unless reducing the vapor pressure of the solution. Okay, so what we can say is the vapor pressure of the solution is lower than that of the initial pure solvent that you add before the addition of the solute. So this leads to what we now call the Raoult's law. Okay, it is based on the same idea of vapor pressure. So the formula is the vapor pressure of a solution is basically equal to the mole fraction of the solvent multiply by the initial vapor pressure, okay, of the solvent. So that is for the solvent. Now the resulting vapor pressure, which is of a solution, is going to be lower. That is basically the argument of Raoult's law. So this is one of those times where you want to make sure you have the vapor pressure of the solvent if you are to determine the vapor pressure of a solution. So it will be a necessity that you get to find that value if you are to find the vapor pressure of the solution. So this is a very simple equation that you need to remember, but understand that vapor pressure is actually vapor pressure of a solution is lower than that of the solvent without the solute. Okay, and we'll be able to determine the vapor pressure by using the mole fraction. So I believe you know how to determine the mole fraction, which is something easy. Just determine the total number of moles. Okay, so total, and then divide the total into the number of moles of the solvent that you want to look at. So if let's say water, you look at the number of moles of water divided by the total number of moles in that solution, you'll be able to get the mole fraction. Now let's move on and now talk about the boiling point. Boiling point derivation. So this already tells you what basically we're trying to say about the boiling point. So of course, what we are trying to say here as well, if you look at boiling point elevation, it means elevation means an increase, right? So what you need to understand is if you add a solute to a solvent, there is an expected increase in the boiling point of that solvent. So the resulting solution has a higher boiling point than the initial what? Than the initial solvent. So what I'm trying to say is, let's say we have water. The normal boiling point of water is 100 degrees Celsius. So if you add a certain solute, you may expect that the temperature of the boiling point will increase slightly. So that difference between the new boiling point and the normal boiling point is what we call the boiling point elevation, the difference. So that implies that if you find the boiling point elevation denoted as that, as a 2, it means that for you to find the new boiling point, you need to add it to the normal boiling point. And that is what basically the boiling point elevation is. So now, under this topic, the boiling point elevation, or the increase in the boiling point, is basically direct proportion to its molarity. Okay, so I don't know how to pronounce that, I'm trying. So it is dependent on so there's a constant, so which we are going to call K subscript B, okay, multiplied by molarity, small letter m. So those the units are for moles per kilogram of a solvent. I believe we talked about the concentration units earlier, so that's what the m denotes. Okay, so this is the formula. So there is a direct relationship between the molarity concentration against the increase in the boiling point elevation. Okay, so of course at times we introduce what we call I. I'll explain later on. For now, just take it as KB multiplied by small letter m. Now freezing point we tend to call it depression because we expect a decrease in the freezing point of after addition of a solute. So freezing point depression. So for the freezing point, delta T as well, which of course shows an increase or a difference or a change in the freezing point. So freezing point depression is equal to, so it's the same idea, it's also has got its own constant, and then again it's also dependent or direct proportion to m molarity as well. Okay, so not much of a difference here. All we are saying is the freezing point will be the freezing point of the solution will be lower than that of the initial solvent. Okay, now the last thing we are discussing or talking about under the corrugative properties is what we're now calling the osmotic pressure. So usually under osmosis is like a permeable membrane that allows the movement of water from a less concentrated side to the side where it is more concentrated. That means where there are more solute particles, okay, from the side where you have got less solute and more of a solvent. Okay, So osmotic pressure as a corrigative property is basically going to be calculated as, so we usually denote it by this symbol, so it is just MRT. So meaning that the osmotic pressure is dependent on the molarity, okay, molarity concentration, that is the capital letter M, that is the gas rate constant, and that is the temperature in Kelvin. Okay, so R we're going to be using 0.0821, that is at the pressure of 80 m liters Kelvin. Okay, and then the temperature there we use kelvins. So that is the formula for the osmotic pressure. So I did also mention to say I'm going to explain what the value of Y basically stands for. Okay, so what is the value of I? So the value of Y, remember we've emphasized to say whenever we are talking about the corrigative properties, we're interested in the number of particles and not what? And not the identity or the type or the material. We are interested in the identity. We are not interested in the identity, we're interested in the number of particles. So therefore, if you have ions or electrolytes, in other terms, these that get to split when you put it in a solution. The simple example you can consider is sodium chloride as a salt. It's going to break into sodium and chloride ions. So those becomes two what? Two ions. And there are certain things that are non-electrolytes. Okay? They don't split. That's what it means. Okay? So in such a case, it will still be the same even if in solution. So we'll take that as 1. And then we'll take that as 2. So what that means, if you are using sodium chloride in a calculation, in the formula, for example, if we're trying to determine this osmotic pressure, we introduce the I, so that the formula becomes IMRT, where I would denote the number of ions that are formed after dissolving. Okay, non-electrolytes, the I will always be equal to a 1. But of course, as some of you have done a bit of some further studies, you realize that of course in sodium chloride it is not usually the reality. Okay, it's not usually the reality, but take it as that, and the I is known as the van 't Hoff factor. So all the formulas with the I become delta T, that is for boiling point derivation. We'll also introduce I, okay, multiply by, so TB, which is a delta change, is dependent on the M as well. So for delta, which is for the freezing point depression, that is, it will also be I, and then KF M as well, and then finally we will have the most osmotic pressure, so which will now be I, and then MRT. Okay, so we've seen I is a very important part of the calculations, especially when you deal with electrolytes, where you'll be able to determine the number of ions that will be formed after dissolving into a solution. So this is an introduction to the corrigative properties. Now in the next video, we'll go basically into details and look at quite a lot of practice questions in a video that is likely to be longer than an hour. So we'll begin looking at vapor pressure as a corrigative property by looking at the possible questions that they can actually give you or ask you under this topic. Of course, we're going to look at all the four one by one, beginning with vapor pressure, and then we'll go to the boiling point derivation, freezing point depression, and then osmotic pressure. Okay, so calculate the mole fraction of that. So this is just like an intro. It's not dealing with vapor pressure, but we need to understand how we can handle the mole fraction in a simple and faster way. So we've been given C2H5OH, okay, in a solution that contains 46 grams of ethanol and 64 grams of methanol. So that's methanol. So we want to find the mole fraction of what? Of ethanol. So we've been given 46 grams of it, and then we've also been given 64 grams of methanol. So how best can we handle that? So obviously we understand that the mole fraction is just the number of moles of that very substance divided by the total number of moles. So we can need to find the individual number of moles for the two. So the question is, what are their molar masses? So we'll just estimate. So for carbon here, so carbon has got approximately 12.01, and then hydrogen will just take it as a 1, and then oxygen is 16. Yeah, and then we've got another hydrogen. Okay, so the molar mass here approximated to be 2 times 12.01, so that's 24.02 plus 5 plus 16 plus 1, so approximately 46.02 grams per mole. Then on the other side, what we have, so we have carbon again. So carbon is 12.01 plus 3 hydrogen atoms plus oxygen 16 plus another hydrogen. So 12.01 plus 3 plus 16 plus 1, so 32.01 grams per mole. So we've determined the molar masses. These are just basic stoichiometric calculations. So let's find the number of moles. So number of moles is the mass divided by the molar mass. Okay, so I'll start from the other side. 64 divided by 32.01, I have 1.999 moles. And then this side, 46 divided by 46.02, that's just like 1, so 0.999. Okay, so that's just like a 1, and then on the other side is like a 2. So how do we basically get to find the mole fraction? So we're interested in finding the mole fraction of ethanol. So the number of moles of ethanol have been determined to be 0.99. So yeah, 0.0, and then we divide by the total number of moles, which is like the addition of the 0.99 plus the other side. Okay, so perform that calculation. So I'm getting a value of 0.33 as what? As our mole fraction. So if they ask you to find the mole fraction of methanol, how would you handle it? So it will be 1.99. So we will only change the numerator. Everything else would remain the same. Now let's look at vapor pressure itself. So here is the first question. The vapor pressure of pure water at 85 degrees Celsius is given to be that. What is the vapor pressure at 85 degrees Celsius of a solution prepared from 100 milliliters of water with a density of 1 gram per milliliter, given 150 grams of that solute, a non-volatile substance? Okay. Can move and look at another question. So at 20 degrees Celsius, the vapor pressure of benzene is 75 and that of toluene is 22. Assume that benzene and toluene form an ideal solution. What is the composition in mole fractions of a solution that has a vapor pressure of 40. Okay, so this is actually another interesting type of a question that we expect. Previously, we've looked at a question where you only have a pure solvent and then adding a substance to it to form a solution. Now, this one is a case where we have two different substances that are coming with their initial vapor pressures. So we have a last question. Under vapor pressure, acetone and methanol form an ideal solution. So at 25 degrees Celsius, the vapor pressure of, so we've been given the vapor pressures of acetone and methanol respectively. We need to determine their mole fractions. So this is a question we've looked at already. So we are told in a solution that boils. So the moment you just see the vapor pressure of a solution, just know that that's, whenever you just see a pressure associated to a solution, that is the resulting vapor pressure of a solution. So therefore, the vapor pressure of a solution was 0.248 in atm. So okay, now talking about the aspect of a boiling point derivation as a colligative property, how do we handle that? So we've got two questions. Just help us understand. Okay, so if 4.27 grams of sucrose, the formula has been given, C12, H22, or 11, are dissolved in 15.2 grams of water, what will be the boiling point of the resulting solution? Now you need to understand basically the formula for the boiling point derivation. Okay, of course we understand that the boiling point derivation is like the increase in the boiling point. So knowing that we have sucrose to be dissolved in water tells us that we're basically going to add the two. Okay, so therefore, knowing that the solvent in this case was water, so the new boiling point is going to be the boiling point of water, which is like 100 degrees Celsius, plus the new one to be calculated. Okay, so let's try to see now what we can do. So for a boiling point of elevation, you know that it's dependent on the constant Kb multiplied by, what do we multiply by? So Kb multiplied by molarity, small letter m. So Kb has been given. Now m has not been given. Of course, there's an aspect of an I which depends on electrolytes. In this case, that one I don't think so. It is not. It's a non-electrolyte substance as sucrose. It can't split into ions. So the I is just equal to 1, not necessary to be short. Okay, but just know, so that in case if you see an electrolyte, you're able to put the value of Y because it does have a very big effect on the solution. So how do you find M? Now M, which stands for molality, it's basically moles of a solute divided by the kilogram of the solvent. So the mass of a solvent. Now in this case our solvent is water. So a good part is we already have the mass of water. So that is, we just need to convert it to kilograms. Now do we have the number of moles of our solute? So our solute in this case is sucrose. So we need to find the molar mass of sucrose. Its mass has been given. We'll be able to get the number of moles. Okay, so what is the molar mass of sucrose? So try to approximate it. So we have carbon, we've got 12 carbon atoms plus 22 hydrogen atoms plus 11 oxygen atoms. So 12 multiplied by 12.01 plus 22 plus 11 multiplied by 16. So approximately the value is like 342.12 grams per mole. Okay, so we have its molar mass, the number of mole, sorry, we've calculated the molar mass. The mass was given as 4.27. So 4.27 grams divided by the molar mass calculated. So the number of moles that we have, 0.012481 moles. Moles of what? Moles are the number of moles of our sucrose there. What else do we need? So let me bring back that formula. So moles over the kilogram of the solvent. So a solvent in this case I've said is water. So 15.2 grams of water should be converted to kilograms by dividing by 1,000. So we have like 0.0152 kilograms. Okay, so 0.012481 divided by that. So we have 0.82 small letter m. Okay, so our Kb 0.512, our m 0.82, our I of course was equal to a1. So multiply by 0.512, so resulting solution is 0.42. That's the boiling point derivation. So for us to find the new boiling point or the resulting solution, we'd have to add it to the initial boiling point of water, which is like 100. So add that to 100. The new boiling point becomes, boiling point of a solution will be 100.4 degrees Celsius. What is the normal boiling point of a 1.21 molar solution of calcium iodide that has a density of 1.92 grams per milliliter? Okay, so this is now a question where you'd have to be very careful. So feel free to pause the video and just try it out. It's as simple as the previous question. Okay, we can look at one more question, and this question of course is attached to the freezing point, depression, and not boiling point. Okay, so what is the freezing point of an aqueous? So you've been given the concentration already in molar concentration, sodium chloride solution. So a freezing point has been given there. At the freezing point, the constant for the freezing point depression has been given. So what do we do to find the freezing point? What is the freezing point of an aqueous? So we'll take an assumption that was dissolved in water. Okay, so we need to find the freezing point. So how do we need to find the depression caused by the sodium chloride? So freezing point depression is equal to I multiplied by Kf multiplied by molar concentration. So I, in this case, sodium chloride will be able to split into two ions, sodium ion and the chloride ion. So 2, the constant 1.86. I can show a bit of some dimensional analysis. So degrees Celsius over molar multiplied by molar concentration. So you notice that the molar concentration will actually get to divide. So resulting solution or resulting answer becomes degrees Celsius. So 2 multiplied by 1.86 times 1, we have 3.72. 3.72 what? Degrees Celsius. Now we need to find the freezing point. So freezing point of water, I believe, is 0 degrees Celsius. So if we have a depression, it's supposed to reduce. So 0 minus that, it becomes negative 3.72 degrees Celsius as the freezing point of the resulting solution. let's continue and look at a few more questions on the freezing point depression practice as a colligative property. So the freezing point of a glucose solution, the molar mass has been given for glucose, is given to be that. So the freezing point is negative 10.3 degrees Celsius. Now the density of the solution is 1.50 grams per milliliter. What is the molality of the glucose solution? So with some of the few questions that are very simple, all they require of you is to understand the colligative property as well as the conversion from molar to molar concentration. So let's try to see what we can do in this case. So I'll try to approach this question as though I don't know how to answer it, to just help you out. So we've been given the freezing point to be negative 10.3. Now we've been given the constant for the freezing point depression, Kf. So one equation that is coming to mind is the freezing point depression, which is of course the constant, the I Van Hoff's factor, which in this case we have the glucose, which does not produce ions. So we just have like the constant itself multiplied by molar concentration. Now one thing that we know is the freezing point is determined as the normal freezing point subtracted by the freezing point depression. Okay, so in this case what I'm trying to say is, since the answer is negative 10.3, if we try to find the actual freezing point depression, plugging in the freezing point to be 0 degrees Celsius there, you notice that you actually end up getting a positive 1. So in short, the freezing point depression is a positive result. The freezing point becomes a negative because we had subtracted from 0 the depression. So we have 10.3 therefore in the formula. Okay, so the freezing point depression is always a positive result. Okay, to show that that's the difference. Okay, although that doesn't make sense, yeah, but it's supposed to be a positive value, knowing that we're supposed to subtract it from the initial freezing point to get the new freezing point of the resulting solution. Anyway, let's proceed. So the Kf is 1.86. So we have small letter m remaining. So we're able to determine the molar concentration actually. So the molar concentration therefore becomes, so we can divide by 1.86 on both ends. So 10.3 multiplied by 1.86, we have 9.5376 molar concentration. What else do we have? So at this point, since we have the molar concentration, all we just need to do is now to convert this guy to molar concentration. Molar concentration. That is all we need to do. We need to convert the value we have to molar concentration, that is. So our molar concentration is 9.5376. Now that stands for moles per what? Per kilogram of a solvent. That's what molar concentration stands for. So it has come as 10.3 as the freezing point depression divided by the constant, which was on like the other side. Okay, So actually the answer is not supposed to be that. I don't know how I got the 9, but it's supposed to be 5.538 after dividing. Okay, so at this point, all we are just doing is now like everything as just a conversion. So we know that from the conversions, where we are going to the molality. So molality is like moles, and then we've got like a liter. And now the liter there is for the solution. Very important. Now, with our assumption that we have a kilogram of a solvent, it becomes easy. So the number of moles we already have, all we need to do is just find the volume of the solution. Now the density has been given. So let's find the total mass to be able to find the volume. So if we can find the mass using the density, we're able to find the volume. So we already have the mass of a solvent. All we need to do is to find the mass of a solute now. So the solute, we've been told the molar mass was 180 grams. That's its molar mass. So the number of moles we already have from the equation there. So we've actually calculated ourselves. 5.538 are the number of moles for the solute. The molar mass, which we are supposed to calculate in most of the cases, has been given as well. So the 5.53 multiplied by the 180, so the value I'm getting is 996.7, so it is like just 8 grams. So we found the mass of our solute by using the number of moles and the molar mass. So we can actually add the number of moles that we found for the solute to the number of moles. So we can actually add the mass of the solute we found to the mass of the solvent. A kilogram is like 1,000 grams. So if we get to add, we have like 1996.8 grams as the mass of the solution. Now the density of the solution was given to be 1.5. Okay, 1.5. So if we get to divide by density, it's like we are saying per every milliliter we're going to have like 1.50 grams. So we're dividing the density into, since you know that the density is equal to mass over volume, so if you're trying to find the volume becomes the mass divided by the density from that formula there. Okay, so therefore our volume comes out to be, so that value there, 1996 divided by 1.50. So we have 1331.18 milliliters. Is there anything else we need? So that can be taken to liters by dividing by 1,000. So we have like 1.331 in liters. So we have our volume in liters. I believe we are now able to look at the number of moles. So our number of moles were what? So our number of moles were 5.538 moles divided by the volume in liters. So 5.538 divided by that. So the result that is coming out here is 4.16 molar concentration. So I think the only two things that we've done here is we just had to relate the freezing point to the freezing point depression, which helps us to find the molar concentration, and then we've just like converted the molar to the molar concentration. We have another question. Here we want to calculate the normal freezing point. So we have the molar concentration there, and then the density has been given. So the molar freezing point or repression constant is given as well. What do we want to find? We want to find the freezing point of a solution. So what do we do? Okay, so at this point we can now look at the osmotic pressure and just finish up the colligative properties practice questions. So calculate the osmotic pressure associated with 50 grams of an enzyme of molecular weight that. So osmotic pressure, we've already established that the formula is MRT. Of course, don't forget there's an I there as well, depending on the presence of an electrolyte or ions. Okay, so the important aspect is you finding the value of M, which is molar concentration. These others, it's not an issue. R is a constant. The temperature is just like always given. Okay, so let's try to see what we can do. So let's try to find the molar concentration. Now, associated with 50 grams of an enzyme, so the enzyme is 50 grams, its molecular weight is 98,000. So we can easily find the number of moles. So number of moles is equal to the mass, 50 grams, divided by the molar mass, 98,000 grams per mole. So grab your calculator there, 50 divided by 98,000. So we have like 5.102 times 10 to the power negative 4 moles. So we have our moles. What else do we need? So we need to divide by the volume if we are to get the molar concentration. So the volume there was 2,600 milliliters, which can just be divided by 1,000 to get liters. In other terms, multiplying by 10 to the power negative 3. So we are dividing 5.102 times 10 to the power negative 4 divided by 2,600, which is multiplied by 10 to the power negative 3. Okay. In other terms, it's supposed to be divided by 1,000 beforehand. So the resulting answer becomes 1.9623 times 10 to the power negative 4 molar concentration, or moles per liter in other terms. So the osmotic pressure becomes, so we have our molar concentration to be 1.9623 by 10 to the power negative 4. Our R constant there is something known as well. So 0.0821, and then our temperature is supposed to be in Kelvin, so add the 273 by the 30, giving us 243 kelvins. So 1.9623 times 10 to the power negative 4 multiplied by 0.0821 multiplied by 243. So I have like 3.9148 times 10 to the power negative 3 osmotic pressure. So the pressure here is in atm, looking at my units for the R constant used. The next question says a 250 milliliters solution. So I have a 250, that's the volume of the solution, containing 21.4 grams of a polymer in toluene. So the osmotic pressure was given to be that at that temperature. What is the apparent formula weight of a polymer? So osmotic pressure, so all these polymers are non-electrolytes, so osmotic pressure is expected to be equal to MRT, the I is equal to 1. Okay. Okay, so let's just have a quiz question. Feel free to just pause the video and just try this one out. So liquids A and B form an ideal solution. So an ideal solution has the vapor pressure to be 1 atm. So the vapor pressure of the pure air is that, and or at the normal boiling point of a solution. So a solution is prepared from 0.25 moles of B and 0.650 mole of air. What is the vapor pressure of pure B at this temperature? So pure B. So one thing that you need to understand is